Oh, right. Cool. Okay. We're 2 minutes past time. Okay. I think it's time to start. So thank you for coming, first of all. Right, we have a very packed agenda ahead of us. So let's start with a couple of quick admin items. So this session is a follow-up to our previous webinar where we discussed building AI agents on AWS. Your feedback indicated that MCP is a hot topic, so you asked and we're delivering, right? The link to that previous webinar will be, I'll share it with you towards the end of today's session. Second, like you already seen, we're recording. We'll share slides, recording, sample code, everything with you a few days after this session. So you'll get a follow-up email from us in a couple of days. Lastly, I do have a couple of team members in the chat, so feel free to ask your questions during the presentation so they can help with answers. I'll also try to leave some time for Q&A towards the end of the session. All right. So without further ado, let's talk about MCP, the Model Context Protocol, right? That's the latest cool kid on the GenAI block, right? So we'll cover many hypothetical and technical aspects of MCP today, right? We'll discuss why do we need MCP in the first place and even build MCP servers together. We'll build at least 2 MCP servers today, right? I hope you're ready for the ride, right? Let's go. So the first big question is, why do we actually need MCP, right? What is the problem that MCP is designed to solve? And if you've been to our previous session about agentic AI, you might see a couple of familiar slides. So we're going to lay our ground toward discussion about MCP. Now, many of us learned about GenAI just a couple of years back, right? When we first saw something like this, an interface to ask questions. It can be Cloud Desktop, ChatGPT, any other similar AI assistant tool. Under the hood, it was pretty simple, straightforward. You had a large language model, also known as LLM, that was trained on a huge volume of data. And you had an interface to that LLM, an AI assistant. For example, ChatGPT, Cloud Desktop, Amazon Q, right? Users were asking questions and LLMs were generating responses based on the training data. This was super fun to play around with, right? You could ask the model to write you a poem about serverless, and voila, it was actually able to do so based on its training, right? It was fun to play around with, but the excitement with the basic stuff was quickly augmented with the realization of the limitations, right? So try asking any LLM a question about something real time. For example, something as simple as, what's the weather right now? The thing is, it doesn't know. This is not something the model that was trained on, right? So all LLMs have what's called a knowledge cutoff date, usually 6 to 12 months ago. So they definitely have no idea what's happening like right now. LLM by itself cannot tell you what time is it or what's the weather. Ironically, in this prompt, it was actually smart enough to recommend me to just look out of the window, right? I found this actually hilarious, right? Good answer. Let's take a couple of other examples, right? Ask it for sales data for your department. Well, the thing is, it doesn't know. But it kind of starts to tell you something, right? I don't have access to your company's sales data or internal systems, right? This kind of gives us some clue of what needs to be done. Let's ask it to fix your code, right? Well, it cannot, since it was not trained on your code. And it explicitly tells you that you haven't provided any code for it to take a look at. So to summarize, first of all, LLMs don't know what they don't know, right? Sometimes they might explicitly tell you so. Other times they might produce fluent, but totally fictional answer, right? So it's important to realize that LLM doesn't know everything. And the second is LLM generate results based on their training and statistical patterns, right? On their own, they cannot perform actions or interact with the outside world, right? So how can we address that? Well, let's run a simple experiment, right? Ask your favorite LLM, how much is 1 plus 2 plus 3? It will happily give you an answer. Now let's make this a little bit more interesting, right? So let's add some additional context. For example, 1 example, 2 is speech, and so on, right? LLM gladly consumed this context and was able to generate a much more suitable response. It even had some, something resembling sense of humor there, right? So let's pause for a second here, right? Does it mean that we can inject the context into prompts to make LLMs smarter? And the answer is yes, we absolutely can, right? The richer your prompt is, the better LLM response is going to be. One of the first ways of using this concept was called RAG, or Retrieval Augmented Generation, right? The idea behind RAG is to have a pre-populated enterprise knowledge base. For example, thousands of legal documents, right, that your company processed over the years, right? Whenever user sends a query, the AI assistant first queries that knowledge base and retrieves information semantically relevant to the query. So you're asking something, AI assistant goes to the database and retrieves relevant information. Once retrieved, it sends both original query and retrieve context to LLM, which generates a response, right? So let's see this in action. Remember this prompt, need final sales data for my department, right? With RAG, this prompt will actually give you a much better response, right? Now you can actually see the data you were looking for, right? With RAG, you can enrich LLM responses with factual historical data. But what if my queries are about something that LLM is not aware of and also cannot be retrieved using RAG? For example, what's the weather in my location tomorrow, right? How do you think it will handle a question that involves, first of all, knowing my location? Moreover, I'm asking about future, right? Future is definitely not the part of training or RAG, right? Now, surprisingly, my AI assistant handled it quite well, right? I got a very impressive response back. Somehow it recognized that I'm based in Austin and managed to get me a weather forecast for tomorrow. And this is true, right? I'm based in Austin right now, and this is the forecast for tomorrow. But how did it know that, right? Like we said, it's not part of the training or RAG, right? Is it hallucinating? And the answer is hiding right here at the very, very bottom, right? So guess what's going to happen if I click that sources button? Obviously, LLM didn't know my location or magically predicted the weather, right? However, my AI assistant is connected to various tools that can help to get this missing information. So what happened is my AI assistant actually browsed the internet, found all these weather forecast websites, found weather for Austin, parsed and aggregated all of the information, fed it to LLM, and generated the result that I'm very happy with. And this is just a very simple example of what's called an agentic AI workflow, right? A multi-step plan of actions that was autonomously generated and executed based on my prompt. Let's see how it works. It all starts with the AI assistant sending a prompt to LLM, but this time also supplying a list and descriptions of various tools it has available. Based on the tool description, LLM can ask the agent to use one of the tools to get more context required to addressing the prompt. This is exactly what happened in the previous example. The original prompt to LLM was get me the weather, right? By the way, if you need some help with that, I have these tools available. So the agent called relevant tools, which might be connected to either enterprise data source or just a simple web browsing capability, right? And performs the required action or retrieves the required result. Browse web, read a file from a local file system, communicate with enterprise API, anything you want. After that, the agent will send tool result back to LLM, right? We're enriching the context. Depending whether LLM needs additional context, it actually might ask the agent to perform this loop several more times. This is dynamic. It's not a pre-programmed workflow. Once LLM is satisfied, it will tell the agent to return the response back to the original user, right? And this is a good example of a simple agentic workflow. So to summarize this section, you just saw what we call an agentic loop, right? This is what agentic systems are all about, agency, right? Agent receives input and some context, calls LLM for reasoning, picks a tool according to LLM response, executes it, updates context, and then the cycle can repeat multiple times. In a nutshell, you can think of AI agents as applications that are calling LLM in loops. The workflow is not predefined. The workflow is adjusted dynamically based on what LLM tells agent to do. However, in order to interact with that outside world, that arrow at the bottom, and provide robust functionality, agents need to be able to communicate with many external tools and data sources, like Salesforce, GitHub, ServiceNow, your enterprise system, or just browse the web to look for weather. Now, the problem is, these tools or data sources, they can have different protocols. Agents might need to access data using SQL or GraphQL, REST, SOAP, gRPC, read from a local file system, hundreds of other different ways of accessing this information. This is a major integration challenge, as you can see, right? With this setup, agent builders are responsible to integrate with every other tool, right, they want to support. That's a lot of work. And tool vendors are highly dependent on agent builders to support their protocols. In my world, this is called a tight coupling, right? A lot of tight coupling between two parties. Coupling is never a good thing, right? And this is exactly the problem MCP is designed to address. Just like HTTP or WebSockets standardized how applications interact with backends, the MCP standardizes how AI applications, agents, AI applications, interact with external tools. It's a simple protocol that allows agent builders to easily support thousands of external tools and allow tool vendors to easily integrate their tool with any AI agent that supports MCP standard. So if your organization wants to make your functionality easily integrated with a vast array of agentic applications, AI agents, you need to start building an MCP layer for it, right? If you want your functionality to be easily accessible by different agents, wrap it with MCP, expose it through MCP protocol. And this can be either your enterprise data source, your corporate system, your fast product, anything, right? So let's examine MCP up close, right? What are the building blocks of this protocol? Now, at its core, MCP defines three types of entities. The first entity is a host. This can be an AI agent or assistant like Amazon Q, Cloud Desktop, essentially an application, right? Some sort of application, agentic application that is connected to LLM. The other two entities are MCP clients and MCP servers. Hosts use clients to communicate with servers. Clients and hosts communicate, servers and hosts, clients and servers communicate using MCP transport. We'll dive into it in a few minutes, right? And MCP servers can communicate with external data sources or services using any protocol they would like. It can be local file system, remote API, anything else you can imagine. Now, MCP is versatile by design. The stack allows for different topologies. You can have clients, servers, and those data sources or tools, everything running locally. For example, an MCP server that enables my MCP host, let's say Amazon Q or Cloud Desktop, to access your local file system or run AWS CLI commands locally on your machine. Important thing to note, local doesn't necessarily mean on your machine. It can be, for example, a EC2 instance. The idea is all of these entities reside in the same place, right? But they never reach out to external networking. MCP also supports hybrid model where client and server are running locally, but the server communicates with a remote data source or service. For example, a local MCP server that invokes AWS management APIs. We have a lot of MCP servers for Lambda, for ECS, for EKS. This is how those MCP servers work. And last but not least is a model where both MCP server and the service it communicates with run remotely. Sort of MCP as a service. That's going to be another aspect that we're going to dive deeper in a few minutes. Okay. MCP is less than a year old, right? It's about 8 months old, I would say, right? The protocol, but the ecosystem grows like a wildfire, right? So this is just a small, tiny snapshot of thousands of MCP servers that community has created in less than a year, right? So important to note, vast majority of those MCP servers are still running locally. We'll go into that soon. Now, from a logical standpoint, MCP spec defines several capabilities. Most common ones are, not the only ones, but most common ones are resources, which enable agentic applications to retrieve additional data, tools, which allow LLMs to perform actions, and prompts, which enable users with reusable prompt templates. All three can be automatically discovered by MCP clients. Auto discoverability is well defined in the spec. It's part of the spec. So today we'll focus primarily on tools, but let's quickly review all three of these, right? So resources represent any kind of data that an MCP server wants to make available to LLMs, right? Such as to clients to LLMs, such as file content, database record, API response, and more. Each resource is identified by its name and URL. You can think of resource as somewhat familiar to what you'll get using HTTP GET requests, right? For example, the resource you see on your screens returns a menu for a particular pizza shop, right? It's easy to understand pizza, right? This example returns text, but it can also be binary data, such as PDF or an image. So once I connect this MCP server to my, agentic application, I can just type my question, hey, what's available on the menu today? And it will know how to retrieve the menu and reply to me. Tools allow LLMs to take actions through MCP servers. A tool, for example, might send a message, update database record, or order a pizza. If resources are semantically similar to HTTP GET, tools are more like HTTP POST requests, right? Tools are identified by tool name, have a well-defined argument schema. Most commonly, tools perform mutating actions or some heavy computations, right? So similar to resources, tools can return either text or binary, like PDF, for example. Prompts is a very interesting component, right? They enable servers to predefine reusable structured prompt templates and workflows that MCP clients can easily surface to users and MCP, right? So you can see here, right, in this example, so this example allows me as a user just to tell my agentic assistant that I want my usual pizza, right? Get my usual. And through the MCP server, this prompt template will ensure that the pizza is prepared to my liking, right? So it's a template, so basically a shortcut to prompt. So now that we've armed with all this knowledge, right, let's actually try to build a simple local MCP server, right? Let's see what are the building blocks. Now, I want to use my AI assistant to get a list of Lambda functions in my account, right? This session is about serverless. So my use case is get a list of functions in my account that are running on deprecated Node.js runtimes. Now, the only problem with this is by default, my AI assistant cannot do it. It doesn't have access to my AWS account. It's kind enough to tell me, which CLI command I can use, but that's definitely not good enough for me, right? So my first use case, I want to use AI Assistant to ask questions about Lambda functions in my account. Before I show you how to implement this functionality, right, before you rush into implementing the whole MCP spec yourself, there is a set of open source SDKs provided by community, collaboration from Anthropic, AWS, JetBrains, Microsoft, many more companies. I highly encourage you to use these SDKs of implementing the wire protocol yourself. Think of it as HTTP. You would use some sort of SDK or framework for HTTP functionality. You probably wouldn't build your own HTTP server or HTTP client. Now, important thing to note, this is evolving protocol, so different SDKs will have different level of maturity and abstractions, right? So your mileage might vary with different SDKs, but all of them are evolving quite rapidly, right? Implementing the latest MCP spec. So let's begin by creating a tool, okay? Now, you've seen me using some Python in the previous step. I'm going to be using some JavaScript here. This is just to show that the language doesn't matter, right? You can use any language. MCP is a protocol. Implementation can be in any language. So let's begin by creating that tool, right? So the first logical step is to give it a name. I'm going to call it list functions. Next, I'll give my tool a detailed description. Now, this part is incredibly important. This is how LLM knows when and how to use your tool. You've probably read the first couple of lines already, but I actually want to focus on bullet number 4. This tool supports optional pagination using the marker parameter. If you see a marker property in the response, you must use it to make another request, right? Well, I have many functions in my account. I want LLM to be able to use my list function tool to paginate. However, I'm not implementing pagination. I'm merely explaining to LLM how it can achieve it. There is a huge difference between implementing and explaining. Well, we'll see it in action. I also defined which parameters my tool supports. In this case, that's the optional string marker. And once again, good description is vital for LLM to properly use your tool. All those descriptions, they are augmented with prompt. They go to LLM. This is how LLM knows when to use your tool and how to use your tool. So the last step is actually, code the tool itself, right? We need to implement the tool. As you can see here, my tool is just a simple wrapper around AWS Lambda SDK that calls the list functions command, right? It doesn't do anything extra, right? It's just calling the Lambda API through the SDK, right? List functions command, and returns the result as is, like literally nothing fancy at all. The next thing is, I need to actually tell my agentic assistant how to use my MCP server. So different assistants that support MCP might have different ways of configuring MCP servers. This is what it looks like for Cloud Desktop, for Amazon Q, for several others. There is some sort of MCP JSON file, and you specify a command and an argument, which in my case is essentially running my MCP server, as a node application. You can see here, it's just a path to my node application. So let's see it in action, right? Time for our first demo, right? So my tool is recognized list functions by Cloud Desktop, and I'm asking it to give me a list of functions running on Node.js. Group by version, tell me which ones are running on deprecated runtimes. I'll retrieve a list of functions, etc. And you can see interesting thing here. I see there are more functions to retrieve. Let me get the rest using provided marker. So pagination is working. I did not code that pagination. I described to LLM how it should achieve the pagination, right? I hope you understand the difference, right? This is awesome, and you will see more of that soon. So you saw the video, right? It gave me a list of functions in my account. It told me which ones are running on deprecated, and it was even kind enough to tell me for best practices, I recommend upgrading your Node 16 functions to at least Node 18 or preferably the latest, right? This is awesome. However, wait a minute. I think I can already spot a problem here, right? So if you're in the Node world, especially building functions with Node.js, you already see a problem here. A few months ago, Node 18 was announced as deprecated. So why does LLM think it's still supported and recommends I upgrade to a runtime version that is being deprecated? Well, because LLM knowledge cutoff date is several months ago. It simply doesn't know about the recent events. Moreover, it recommends upgrading. Recommendation is nice, right? But here at AWS, we love to do things, right? So we call it bias correction. So I'm going to enhance my use case. My new use case is going to be, I want to use AI Assistant to safely update functions to the latest runtime version. So let's highlight important pieces here. Safely is important because a function might start crashing after a runtime upgrade, right? So how do I deal with that? Update means my agentic workflow is no longer read-only. It will actually take actions. Latest is important because, knowledge cutoff date. I want to use the runtimes that are latest today, not last year, today, right? I'm not going to bore you with how I implemented all the other tools. The code is on GitHub. I'll share it towards the end. Let's just see what these tools are, right? Now, the top one is quite interesting. Like we said, 12-month-old runtime support info is not good enough. So the get runtime info tool will retrieve Lambda docs page, parse it, and provide my agentic assistant and LLM with the most up-to-date information about runtimes as of right now, right? The other tools are similar to list functions, just slim wrappers around Lambda SDK calls. However, you might have a question, why do I need the invoke function tool here, right? I totally can understand update, but why invoke? That's a really good question. Let's quickly take a look at the description of update function tool, right? The description explains how and when to use this tool, but take a close look at bullet number 4. After updating a function runtime, you should invoke the function to validate it still works. If it doesn't, roll back. Again, I'm not coding the rollback logic. I'm describing it to the LLM. What happens next is quite fascinating. Let's take a look at this demo. So I have a function where I'm faking crash if Node.js version is 22. I'm going to fake a crash. My source function is a Node 18, right? So I want to upgrade it. So you can see that my agentic assistant already picked up my new tools, and we're going to start exactly in the same place where we were last time. Give me a list of all functions in my account that are running on deprecated or soon to be deprecated Node.js. You already saw that, right? So it starts to retrieve a list of functions. It's smart enough to paginate, right? But that's like last year news. We already saw that 10 minutes ago, right? What happens next is quite interesting, right? So it identified functions running on runtimes. Now you can see here, it already knows that Node.js 18 is soon to be deprecated. So it retrieved the latest information. Now it can make more intelligent decisions. And it's also aware of what it can do. I recommend updating those functions to newer versions like 20 or 22. So let's see if my invoke is working. Can you check if demo function 1 is working? That's the function that I'm using. Yes, it invokes that function, and it says, yep, your function is working. I got HTTP 200 back. And once again, it suggests to upgrade the runtime. And now, in a very nonchalant way, I'm going to say, yeah, update it to the latest Node.js. From this point on, hands off keyboard. Let's see what's happening. So I'll update this function to the latest Node.js runtime version. First, let me get the current configuration. Why does it need the current configuration? Because it knows that there is a chance it will need to roll back. Now I'll update the function to the latest version, which is currently 22. So it updated the function to the latest Node 22 from 18 to 22, right? Let's verify that the function still works. It invoked the function using the invoke function tool and tells me it looks like we encountered an error, right? Abandoned ship, because this is what I expected. This could be due to compatibility issues. Let me roll back to a more stable but still supported runtime, Node 20. So we started with 18. It tried to upgrade to the latest 22. It discovered a problem, and now it attempts to downgrade one version, not to the original 18, but to 20. It's smart enough. It was actually smart enough to do that. Right, so it downgraded to Node 20. It validated that the function is working, right? And let me go back, right? And it gives me a result, right? So this is what you can do with MCP servers and LLMs. LLMs are there to reason, to make decisions based on the context they know, and MCP allow LLMs to perform actions with the outside world. We'll talk about MCP transports in a moment, right? But one thing I want to note that, like I said, the code is going to be on GitHub, but we've also released quite a lot of official MCP servers from AWS. We have Lambda MCP server, official one. We have ECS, EKS, quite a few more. So if you're looking to interact with your services and applications running on AWS, I highly encourage you to look through our official MCP servers. I'll have a link towards the end. All right, so MCP transports, right? Or how do clients and servers communicate under the hood? This is an important part, right? How does it work under the hood? Because, yeah, we'll build those MCP servers in a moment. MCP is a JSON-based protocol. It defines 3 types of messages in general: request, response, and notification. Now, do not confuse this with HTTP request and response, right? MCP request and response it's just JSON object, as you can see on your screen. Those JSON objects can be transported using multiple different ways, not just HTTP, right? Important thing to note is both clients and servers can send messages in either direction. To make it very, very explicit, servers can send requests to clients. I know it's mind-blowing, but bear with me, right? Transport is the channel that clients and servers use to exchange messages. MCP spec defines two types of transports. The first one is STDIO, which is used in standard input-output streams on your system. It's commonly used for integrations with local MCP servers and CLIs. This is where MCP started. I would say easily over probably 95% of all MCP servers today are using STDIO. My previous example used STDIO. But the spec also defines streamable HTTP transport, which MCP clients and servers can use to communicate remotely over HTTP. This is one of the latest additions to MCP spec, and we'll be talking a lot about it in the next 10 minutes, right? You can also do custom transports, but these two are kind of built into the spec. So let's start by exploring the STDIO transport. It's super simple. You saw it in action in previous section. So when your MCP host is configured with an MCP server, it will start by launching that MCP server as a sub-process, literally a standard OS sub-process. It will then create an instance of MCP client and use standard input and output to communicate between clients and server, right? Basically send those JSON objects you saw in the previous slide. This is super simple, super fast. Everything is happening on your system. It's just communication between two processes, right? And you can obviously have more than one pair of clients and servers running at a time. Each server will run in a standalone sub-process. But let's switch gears and talk about the streamable HTTP transport, because we want to run those MCP servers remotely on AWS. This transport supports two modes, with or without SSE connection. We'll start with the former. So since MCP server is running remotely, MCP host is no longer responsible for starting it. The host assumes that server exists and uses standard HTTP post requests to communicate with it. So you configure your host with the URL, and this is how communication works. So imagine you have your request JSON object, right? A MCP request that you send from client to server using HTTP post. This is where things start to be interesting. The server will process the request and generate a response. In order to send that response back to the client, the server will, by default, establish an SSE connection with the client. SSE stands for Server Sent Events. It's a stateful, rather simple technology that allows servers, to send events to clients. That's right, from server to client. It's one direction only, not both ways. And this is a persistent connection. So the server sends a response back to the client and then closes the connection. You may have a question at this point, why did server need that complexity? Why would you need that, right? Why would you use SSE in the first place? Why couldn't you just send the response back as a standard HTTP response? This is a very good question. To answer it, let's examine an advanced scenario supported by the MCP spec. So we'll start the same. Client sends a request to the server. The server accepts that request, but quickly realizes that it will take time to generate the response. It's not immediate. So instead of keeping the client guessing what's taking so long, it might generate a notification payload saying, hey, I'm still working, don't give up on me. Then the server will create that SSE connection and use it to send notification to the client. This can be, keep on waiting. This can be, for example, hey, I have a new list of tools, refresh your list of tools, right? And after some period of time, let's say the server can realize that it actually does not have enough information to process the request. It might need more input from the user, or it might want to make a request to LLM through client, right? Like the MCP host is connected to LLM. So it will generate a request and send it to the client. And after some time, when client has processed that server request, it generates a response, let's say collected additional information from the user, but it cannot send that response back using that SSE channel. Because like we said, it's a one-way connection. So the client will send a new post request to the server, to which the server will reply with HTTP to accept it. Only after this extended exchange, the MCP server has finally generated the proper response to the original request. The server uses existing SSE connection to return the response back to the client, after which it closes that connection. As you can see, this is a multi-step streaming protocol, hence the name, right? Streaming HTTP. So once again, I urge you to use the official MCP SDKs instead of implementing it yourself, right? So you don't want to implement this whole ping-pong. The good news, however, is that SSE part of the protocol is actually optional. You can also build MCP servers that do not require persistent connections. You do lose some of the capabilities, like you saw the ones that you saw on previous slide, but in return, you can build fully stateless and super easy to scale horizontally serverless MCP servers. So let's see how it works. Clients still use POST requests to communicate with servers, but instead of opening an SSE connection to reply, servers just send response back as a plain HTTP response body. This is not a workaround. This is officially defined workflow in the MCP spec, right? And this allows us to build very robust, stateless MCP servers that are much easier to scale, which is exactly what we're going to do, right? So let's start building a remote MCP server that is going to run on AWS, right? So as you've seen before, your MCP servers are essentially just applications running on AWS. MCP, it's a JSON-based protocol on top of HTTP. You can run them in a variety of different ways. If you're looking for simplest and most managed way to run MCP servers on AWS, I recommend you evaluate Agent Core Runtime and Agent Core Gateway capabilities, right? We launched them a couple of weeks ago, right? They allow you to either run your custom MCP server or even wrap your existing Lambda functions or REST APIs with kind of MCP proxy, right? But if you're looking for more do-it-yourself flexibility, right, where you control more things, you can run your MCP server, right, on pretty much any kind of compute you're already familiar with. You can run your MCP servers on Lambda functions, ECS, EKS, EC2, anything, right? It's just an application. So in this session, this is about serverless MCP servers. So we'll explore two services, Lambda and ECS, but keep in mind, your MCP server is just a web application. So Lambda, let's start with Lambda. It's a highly ephemeral compute, so it would be a great fit for stateless MCP servers. ECS, on the other hand, provides long-lived containers, which allow you to run both stateless servers and servers that do support persistent connections. So let's start with Lambda, right? This one is much simpler to implement, right? Let's start by building a stateless MCP server on Lambda. We're going to be building MCP server for one extremely sophisticated MCP tool, right? The tool name is ping, and as you can guess, it will return a pong, right? As simple as it gets. I don't care about the actual functionality of the tool. That's why I'm using something very simple. I care about how do I implement this end-to-end. So we'll start simple with two usual suspects. We'll use Lambda to run the MCP server and API gateway to expose that MCP server to clients. I'll share the links to the source code. You'll get all the samples we have. It's all on GitHub, right? But in the meanwhile, I want to show you the most important implementation pieces, right? So first of all, you need to decide whether you want stateful or stateless MCP server when you're starting to code, right? And whether you want to return JSON right away or use SSE service sentiments. You can see various configuration options on your screens. This is Python. It might look a little bit different for other languages, right? So the SDKs are a little bit different. But since we're building a stateless MCP server, I'm going to use this configuration, right? I want my server to be stateless, and I want it to return JSON right away without SSE connection. So MCP ecosystem provides a very useful tool called Inspector for testing MCP servers. We'll use it to test that everything works as expected. You can see here that the tool is using the streamable HTTP transport and connecting to an endpoint exposed using API gateway. So Inspector is capable of easily retrieving the list of tools. I only got one tool, ping. Remember, discoverability is part of the protocol. So you don't need to implement it. You just define your tools like you saw in the previous examples, and Inspector will retrieve that list of tools and what are the parameters automatically for you. I only got one tool called ping. And when I call this tool, I'm getting the response I expect on, right? I do add like a log stream name there, right? Just to see where I can find my logs. But essentially, this is a proof that, I can run MCP server on a Lambda function. It's pretty straightforward, and it works pretty much out of the box. Now, this was all good and fun using SDKs to build servers, right? And deploying them to cloud. But what about all the operational aspects, right? What about observability? What about security, governance, CI/CD, many other things that you need to think of when building applications in cloud? The good news is, like I said before, MCP servers are essentially applications. So everything you know about building serverless applications and APIs on AWS is still very much applicable, right? A small caveat. Some things, for example, like authorization workflows, right, are still evolving. So MCP is still a very young spec. It's still evolving, right? So do, follow the evolution, use the latest SDKs, and you can already leverage tons of AWS wisdom that we publish almost weekly, right? So for example, this is where we start, right? Simple. API gateway goes into our MCP running on Lambda. So how do we secure this? Well, how about adding an API gateway authorizer, right? Now, the request coming into my MCP server, I can actually authorize them, right? Validate that users are authenticated and authorized to access that. You want to add network security? Well, you can enable throttling in API gateway, right? Use certificate manager, use a web application firewall, all the goodies you're familiar with on AWS. Do you want to integrate with the wider AWS ecosystem? Well, you sort of already are integrated. So since MCP server in this scenario is running on a Lambda function, right, you can use the vast ecosystem of AWS services, as well as reaching out to third-party endpoints, right? And all of this is still protected by IAM, monitored by CloudWatch and X-Ray, and so on. So to give you one, very straightforward example, here's my MCP server observability. I got metrics, I got logs, I got traces, all of that automatically, just because I'm using AWS services that already provide all of this functionality, right? So let's see what changes if I need to build a stateful MCP server, which will run on ECS party tasks. So stateless MCP on ECS will work exactly the same as Lambda, but stateful is a little bit different. We got a new problem to tackle, right? Persistent connection. So we'll use ALB to expose MCP servers to clients. Can we do the same with EC2 or EKS, not just ECS? Yeah, obviously we can. This session just scoped to serverless technology, right? And let's see what is that new challenge we need to address to create a stateful MCP server. Now imagine your MCP client sends its first ever request. That request will flow through the ALB and eventually will be processed by one of the tasks. I highlighted that, right? Running the MCP server. That's the instance of my MCP server. By default, ALB will randomly pick a task to serve that incoming request. So the load will be evenly distributed across all the tasks in my ECS service, right? This works great for stateless applications, but here we're building a workload with state and persistent connection, right? As you recall, during my first request, my client has established a connection with one of these tasks. So if I send a new request, and it gets to a different task, that task is not aware of previously established connection. So it will reply with HTTP 400. In order to make it work, I need to ensure that my ALB is connected with sticky sessions, and my client actually supports cookies, right? But most clients do support cookies today, right? So all requests from a particular client will be forwarded to exactly the same ECS task. Now, how do I achieve this? Well, first of all, you enable stickiness in your infrastructure as code configuration, creating the ALB target group. You can define type and duration, right? So with cookie-based stickiness, the ALB will generate a cookie that can be used for sticky routing in subsequent client requests. And when you're configuring your MCP server, you ensure that you do not run it, that you do run it in a stateful mode, not like we ran Lambda, but in a stateful mode with SSE support. For Python SDK, that would be the default setting. So, you don't need to set it explicitly. That's the default for Python SDK. So we talked a lot about technical stuff. Let's actually see some additional demos. So to reiterate, you'll get the slides, you'll get the source code, you'll get everything, right? Everything you see here in my demos, you'll get it. In this first demo, you'll see a travel agent communicating with the bookings MCP server. Both run on Lambdas, both are exposed using API gateways, both are protected by Lambda authorizers. Note, keep in mind the MCP tools, you'll see them in action in just a few seconds. So let's see the demo. So since my agent is protected, I'm using Cognito here, I need to log in first. Okay, so I'm logging in as Alice. You can see that my agent has recognized me as Alice. And now I'm asking, I want to travel to for a party in Paris. The thing is, my corporate travel policies kind of forbid that, right? So what happened in the background is agent reached out to MCP, and MCP returned travel policies that do not allow traveling to Paris. Okay, I'm trying to something different. Book me a business trip to New York. Now my agent is looking for any violations. No violations found. It reminds me about the car options that we have, right? And it asks me for additional details. That it cannot book me a trip before I tell it, when the trip starts, how long is the trip, right? So it starts next Monday. It lasts for 3 days, and I'm trying to cheat the system again. Rent me a Mercedes because I know that luxury cars are forbidden. So right now, the agent goes to MCP server trying to book that trip. And according to policies defined in MCP, here's the summary of my booking. The car is Toyota. The hotel is whatever New York accommodation. And here are the dates, right? And it tells me I book you a standard sedan. I can confirm the travel. Once again, the agent behind the scenes would go to the MCP to actually call that book hotel and book car, rent car tools, right? So I'm communicating with my agent, but the booking functionality and the policy functionality is not implemented in the agent. It's implemented in external MCP server, which my agent communicates with for this seamless experience. But, what if I don't want to build my own agent, right? What if I want to get to a point where my MCP server can integrate with any existing AI assistant or agent, right? For example, Club Desktop. That's the beauty of MCP. It's a standard, right? If you have any application that supports MCP standard, it should be able to communicate with your MCP server. So to give you an example, right, let's use the same MCP server, right? But this time we're going to consume it from the Club Desktop. So first I need to connect to that MCP server. I'm going to call it booking MCP, and I'm going to give it a URL, where that server runs. Okay, you can see it's registered. So now I need to authenticate because that server, remember, right, it requires authentication. So I'm going to authenticate with some MCP user, right? Same using Cognito here. You can use any other identity provider. Now you can see that my MCP is connected and also authorized. So I can go back to the chat interface and I can ask, what are my loyalty points, right? Or something else that can be retrieved through MCP. And now I'm communicating with my travel booking system through Club Desktop. And this can be pretty much any other, agentic tool that communicates using MCP protocol. Okay, so this specific demo, right, integration with Club Desktop, this is something that we're finalizing, and I'm going to share a link, GitHub link towards the end. This specific demo source code is not there yet. It will be there pretty soon, but all the previous demos, they're already on GitHub, right? This one we're still finalizing. All right, we're getting close to the finishing line. We got about 9 minutes left. So before we wrap up, I do want to cover a couple of advanced patterns, right? Because this is what I expect to be the topic for our next discussions, next enablements. This is what we've been talking about for quite some time now, right? An application that is running MCP client, that's your agent, and communicating with another application that exposes MCP server endpoint. However, that purple application that implements the MCP server might also use some, agentic logic in it. and would want to communicate with yet another MCP server. So think of it as, HTTP. Any HTTP server might also have a component that uses a different HTTP client to communicate with yet another downstream system. And that downstream system might have a component that wants to communicate with yet another downstream system, right? So you can use MCP for that as well. Composability is an important part of MCP. As you can see, it allows you to compose MCP layers, just like you would compose MCP servers. But also keep in mind, MCP is a protocol designed for agents, for agentic applications to communicate with tools. So essentially, the two applications, with MCP clients you see on their screens, they're agents, right? And we're, just implemented our first kind of simple multi-agent architecture. So to show you the art of the possible, right, let's make it less about the protocol and more about business use case. Consider a scenario where you, a user, want to buy a good pair of running shoes because you want to participate in the Boston Marathon. Now, this marathon happens in April, and if you're from Boston, you know that the weather can be a bit unpredictable. So you want to do some research and analysis before you buy. So you ask your agentic assistant, which will orchestrate the process, to find you a good pair of shoes. And that assistant will start by communicating with a weather forecast agent, which exposes its functionality as a remote MCP tool. So you have an agent, but it's exposed through MCP protocol. That forecast agent can use MCP server that communicates with, let's say, weather.com or any other forecast site, right? As you can see the tools there. Once weather forecast is retrieved and processed, your orchestrator reaches out to research and analysis agent, again, exposed as a remote MCP tool, right? Which will consume the weather analysis retrieved previously and start searching various online forums for information about, best shoes suitable for expected weather. And once that agent identifies the right shoes, your orchestrator can go to a shopping agent, which can use something like Amazon.com MCP, which I completely made up. I'm not aware of Amazon.com MCP, right? To find the best deal on these shoes and, add them to the cart and actually buy them, right? This is how multi-agent systems collaborate, right? This is how you can use MCP to facilitate this collaboration. And based from, feedback I'm getting so far, we do plan to have a separate enablement similar to this, talking specifically about multi-agent systems. So this has been quite a journey. We need to start summarizing. All the samples you've seen today, much more is available using this link. I'll share it. You'll get the slide. Don't worry. The only exception was that club desktop integration demo. It will be in the same repo pretty soon, right? As MCP spec evolves, we're planning to continue evolving the samples and reference architectures as well. Moreover, AWS teams are collaborating on various ways to simplify building MCP servers on AWS, and this repo will reflect that as well, right? MCP is still somewhat early stages and has a very long way to go, and we'll be there leading these efforts. So quick recap of best practices for building MCP on AWS, right? The spec is very young and it's evolving rapidly. So instead of implementing it on your own, use the official SDKs and follow the spec evolution. This will make sure your MCP servers using the latest capabilities compatible with widest range of agents. Other practices are based on the fact that MCP servers are pretty much web applications. So everything you know about building web apps on AWS is applicable. Design for scalability and performance. Consider whether you need your server to scale horizontally, whether you want it to be stateful, stateless. Consider using serverless due to their out-of-the-box availability and scalability. Implement robust network and application security, and you're getting a lot of that just by the virtue of building on AWS. Track the spec evolution, adopt latest security practices, right? Being very honest at the moment, right? There are still several areas which are still kind of in flux, right? But every new version of MCP protocol brings, additions, right? Basically fixes things that we definitely want to evolve. Don't forget about comprehensive monitoring and logging, right? MCP servers are servers. You need to be able to track their telemetry, operational aspects. You want to be able to detect potential issues early and fix fast. So bottom line, apply your existing knowledge as well as well-architected framework. Once you get these slides, you will see a bunch of links you can use to continue your journey for building MCP on AWS. As I mentioned, we'll share all of this content in a follow-up email in the next few days, right? Maybe probably tomorrow, maybe early next week, right? So don't worry, you'll get all of this. And with this, the last thing is we highly value your feedback, right? This session was designed based on the feedback we received in previous webinars. So let's continue this tradition. Please fill the survey so we would know where you are in your agentic journey and how we can help you to accelerate. I'm going to paste a link to the survey in the chat window as well. Give me just a second, chat. Okay. Okay, yeah, the link is there. So please do, fill the survey. This is what's helping us to make our content better, to, know which direction we need to go and help you better to be more efficient with onboarding your agentic applications to AWS.